So this is we're not doing, remember doing identities? Grade 11? How many people love identities? What? Nobody? Identities are awesome. How many people hate identities? Oh dear. Why did you take this course? Okay, so that's next unit. You should try, like anything in life, especially if you're forced to do it, you should go into it with an open mind. So when we do identities, try to go into it with an open mind. They're actually not that bad. I had somebody last year who said in grade 11 he was terrible at identities. Like he did really well at everything else. It was the one thing in the whole course. And he really buckled down. He really worked hard, asked a lot of questions. We worked together. And by the end of it, he was fantastic. Like awesome, as good as anybody else in the class. So you can change those things around. It's a different way of thinking. It's a different kind of a question. But anyway, it's doable. Identities are doable. Okay. So we're not doing identities in this unit. It is the next unit. We're going to do a little bit of identities, a little bit of a refresher, a nice little thing right now to kind of get our ball rolling here and remind us of a couple of things. So here's the conjecture. So remember, sine is opposite over hypotenuse. Whoops, printing mistake. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So my conjecture is that tan theta is the same as sine theta over cosine theta. How do we do this? Remember, with an identity, you have to do the left side separate from the right side. And again, this is not something you need to worry about. This is not going to be tested on right now or anything like that. It's just for fun, because identities are fun. And so one of the rules for identities, or one of the, not rules, where you don't really go based on rules, but like strategies, tips, strategies, kind of things, places to start is we usually look at the more complicated side. So I would say the right side's more complicated in this case. So I'm going to start working on that side. How can I rewrite sine just based on what we had up here? Easy question. Thank you. So I'm going to replace sine with opposite over hypotenuse. How do I replace cosine? Somebody else? I know it's an easy question. Adjacent over hypotenuse. Fraction math, which we're all getting good at. Dividing two fractions. Here's one of the fractions, here's the other. How do I divide fractions? You flip the fraction you're dividing by and you change it to multiply. So this is opposite over hypotenuse times hypotenuse over adjacent, right? So I flipped the bottom fraction, adjacent over hypotenuse, and we're multiplying. And what happens? Hypotenuses divide to 1, and I get opposite over adjacent, which is tan theta. Awesome. We did it, right? Simple little proof, but it does remind us that this is something that you know. You remember this. This is an identity from last year that you should know. Maybe you should, like, you wouldn't have remembered it on your own, but now you remember it. Tan theta is sine theta over cosine theta. So what about for cotangent? You could do the exact same thing. I'm actually going to leave that one to you. I would say try it. Do it the same way. Like, we know cotangent is the reciprocal of tangent. So one way that you could do it is cotan theta, and then that's equal to 1 over tan theta, which is equal to 1 over sine theta over cos theta. Like, you could do it this way, or you could, to prove it, or you could do it this way, but it would just be upside down from the first one. So I'd challenge you to try that. But if you think about it, that could be part of your homework. You're not going to be too much homework tonight. But if you think about it, cotangent is a reciprocal of tangent. So if tangent is sine over cos, cotangent is cos over sine. Like, that's pretty obvious. And there's lots of different ways to think about that, right? There's lots of different ways. I mean, we could do the proof, right? There's lots of ways we can think about that. And all those ways, the more ways that you make connections, the better problem solving, the better your understanding is going to be of the bigger picture. And trigonometry, especially angles and standard position, that kind of stuff, is all about the bigger picture. Okay, making connections between everything. So I could memorize that cotangent is cos over sine, and that's fine. But I also really want to be able to make that connection about reciprocals and those natures and things like that. Make sense? You happy with that? Okay, what we're going to do is actually, you know what, let's skip this. You could do the triangles and get the exact answers, but what we're going to do, I think, is use decimals so we can actually plot this. So what I want you to do, this is counting by pi by 12. So this is cool. Just watch for a minute because we are going to start graphing, and we've done a little bit of this. So this is 0 pi by 12. This is 1 pi by 12. This is 2 pi by 12. This is 3 pi by 12. I'm not going to do all of them. This is 4 pi by 12. This is 5 pi by 12. We got to fill in the top here first. 2 pi by 12, how would I reduce that? Pi over 6. I can divide 2 and 12 by 2. So it's pi over 6. 3 pi over 12 reduces to pi over 4. 4 pi by 12 reduces to pi by 3. 5 pi over 12 reduces to, yeah, nothing. That's right. It is what it is. 5 pi over 12. So finish that first line as best as you can. I will put the answers up as we go as well, so you can make sure that they're right. And then what we're going to do is punch these into our calculator, okay, and fill in the gaps for sine and cosine. So what I would do, I'm going to do sine of pi by 12. So make sure your calculator's in radians. Sine of shift pi divided by 12 equals, and I get, you probably only need, I would keep 3 decimal places. You probably only really need 2, but let's try to get 3. Let's go for 3. So 259, and then you can do 1 divided by that answer to get cosecant. So that's 3.864. Okay, I'm going to give you a few minutes to start filling that out, and then we will resume together. So hopefully you've got all of this, all the values written out. Hopefully you've noticed the patterns that arise, and the patterns do definitely fit our understanding of sine and periodic functions in general. So I've got these 5 values, and we notice that they repeat, and what's interesting is the order in which they repeat had better fit our understanding of the curve. So these are going up, approaching 1, as sine goes up and approaches 1, and then they go back down and approach 0, as sine goes back down and approaches 0, and then they're negative, right? And these are quadrant 3 and 4 angles, which are negative for sine, which makes sense. These are quadrant 1 and 2 angles, which are positive for sine, so it all makes sense. Everything in trigonometry, angles in standard position, it's all about the big picture. So the more connections you make, the better off you are. And then when we look at cosecant, the values, first of all, notice that what is the reciprocal of 0? So let's say 0 over 1. Reciprocal is 1 over 0. Undefined, can't divide by 0. We know that from grade 9. Another thing to notice, when a number is positive, its reciprocal is positive. Positive, positive. When a number is negative, its reciprocal is negative. Okay, really important. And the last thing that's really important to notice is the reciprocal of 1 is 1. The reciprocal of negative 1 is negative 1, right? What does all that mean? That means if I draw both of these graphs on both of these curves on the same grid, like we're about to do, okay, when sine is positive, which is in this area, cosecant will also be positive. So it'll be above the x-axis somewhere. When sine is negative, cosecant will be negative, okay? And they will meet at 1, so that they're both going to move towards 1. Let's take a look at what the graph actually looks like. Okay, so here's sine, first of all. Notice that it starts at 0, and then it goes up to 1, back down to 0, down to negative 1, back up to 0, and then repeats. So what happens if I add cosecant? Well, if sine starts at 0, when I get just above 0, what happens to cosecant? Well, it's really big. That makes sense because the reciprocal of a very small number will be a big number. What's the reciprocal of 1 over a million? A million. Okay, something smaller, what's the reciprocal of 1 over a billion? That's smaller than 1 over a million. Is a billion, that's bigger.
So when sine gets really small, cosecant will get really big, and vice versa. Now, as sine approaches 1, what happens? Cosecant also approaches 1, because they're both equal to 1 at pi by 2, because they're reciprocal. Reciprocal of 1 is 1. Okay, and then as sine approaches 0, what happens? Cosecant goes back up to infinity, and we have an asymptote, because you can't actually take the reciprocal of 0. So cosecant doesn't exist there. It's very important. It's an asymptote. And that's something that you should be able to communicate. Where are the asymptotes of cosecant or secant? And that may seem confusing, but it's actually very easy. Where do the asymptotes of cosecant occur? Wherever sine is 0. So there's also an asymptote here. It's just not on this graph right now. There's an asymptote here. Where's the next one going to be? When is the next time that sine is 0? At 2 pi. So let's watch. So notice how cosecant here is negative. It's a purple curve, right? Because sine is negative, the reciprocal is going to be negative. And then as sine approaches 0, cosecant goes to negative infinity because sine is negative. Okay, and look at it continues. The pattern continues. So once you know the sine graph and you have a little bit of understanding about reciprocals, and you do a little bit of work with this, you know cosecant. It's actually not that complicated if you just relate it to sine. Okay, they meet at 1. When sine is 0, cosecant doesn't exist. And I know that it has this U, upside down U shape. And then I can think about where it starts and where it goes to. If I look at secant, let's wait for it to come up here. Okay, so this is part of your homework. Your secant graph should look like this after you've actually plotted the points. Here we go. If we look at secant, what happens? Well, cosine starts at 1, so secant starts at 1. And cosine is moving toward, cosine is the orange curve, it's moving towards 0. So secant is going up to infinity. So watch. See? And then again, as cosine moves towards 0, secant moves towards infinity. Okay, and so on and so forth, and it repeats. So if I start here, this looks like cosecant. From here to here looks like cosecant. But it's shifted. Just like sine and cosine, there's a lot of parallels between them, but there's a phase shift as a difference between them. Cosecant and secant are the same. Otherwise, they have the same look, and students do have trouble figuring out where it starts, where it finishes, that sort of thing. But you need to relate it to the graph sine or cosine that you already know very well. Okay. So then you can do secant as your homework, fill out all of those. So we're going to fill out the information for cosecant. Part of your homework will be doing it as well for secant. Okay. Amplitude is, there isn't one, the max, it has no max, it goes up to infinity, has no min, goes down to negative infinity, so there is no amplitude, right? Not applicable, none. The period, so if we start here, okay, we've got this part of the graph, it's still a new part of the graph, and then it repeats, so it takes 2 pi, just like sine, just like cosine, the period is 2 pi. Phase shift, again, this is a parent function, so none or just 0. Vertical translation, parent function, so 0. What's the range? This is interesting. Y is an element of the real numbers such that, let's take a look. Domain would be even a little bit trickier. It's something to think about. Domain, it exists everywhere except for where there are asymptotes, which is at multiples of pi. So pi, 2 pi, 3 pi, 4 pi, negative 2 pi, right? That's where it wouldn't exist in terms of domain. In terms of the range, it's negative infinity to 1, and sorry, negative infinity to negative 1, and infinity to 1, or 1 to positive infinity, right? And it doesn't exist between those values. So from negative infinity is less than y, which is less than or equal to negative 1, because it does equal negative 1, and 1 is less than or equal to y, less than infinity. Where does it increase? Let's go back. Let's just talk about in the first cycle, one cycle, okay, 0 to 2 pi. So from here, it is increasing, whoops. From here it is increasing, and it's still increasing, but it's not increasing where it doesn't exist, so that's going to be a little bit tricky. It's decreasing here, and it's decreasing here. So it actually has 2 intervals of each. So how would I write that? Okay, so where does it start? increasing. It starts increasing at 1, but it's not increasing at 1. So we would say in interval notation, this would look like this. 1, 2, 2, sorry, not 1. That's its y value. What's the x value there? Pi by 2. So from pi by 2 to pi, bring that back up, to pi, okay? And it doesn't include pi either because it doesn't exist at pi. And then still from pi to 3 pi by 2, where it stops increasing. Now, some people might say, why do I have to write it twice? Couldn't I just do from pi by 2 to 3 pi by 2? That would include the value of pi, and it's not increasing at pi because it doesn't exist. You have to write it as 2 intervals. Okay? Or if you did it in set notation, that would be pi by 2 is less than x, which is, or theta, depending on how you're graphing, is less than, whoops, not less than or equal to, less than pi, and pi less than x less than 3 pi by 2. Okay? So depending on your notation, that's how it would look. Intervals decrease are the other ones. So again, it doesn't exist at 0, but it starts decreasing there, and it decreases until pi by 2, where it starts increasing, as we saw. Okay? And then again, it starts, and then it doesn't, while it's increasing in the middle there, and then it starts decreasing again here at 3 pi by 2 to 2 pi. And if you sort of add up all those intervals, except for where it doesn't exist, they would add up to the whole period, 0 to 2 pi. So do that for secant, and finish your graph for cosecant if you're not all the way done. You can plot the points is a good idea, but really think about the points as a reciprocal of sine, and think about the nature of the curve compared to sine. Last thing I just want to go over quickly is this demo for tangent. So tangent, remember, is sine over cosine. This is a little bit trickier, but it is something we're going to do later in the course as well. So if I look at sine over cosine, let's get these started. So the orange curve is obviously sine, and the purple curve is obviously cosine. Okay, so if I look at those together, sine over cosine, what would that look like? Sine starts at 0, cosine starts at 1. What is 0 over 1? Sine over cosine, that's tan. 0 over 1 is 0, so tan is going to start at 0. Sine and cosine are equal to each other at pi by 4, right? So at pi by 4, see pi by 1 pi by 4, 2 pi by 4, 3 pi by 4, 4 pi by 4, there's pi, equal to each other. So sine over cos, when they're the same, something over itself is 1. So tan is this new curve that's just popping up here, is equal to 1 at that point. And as sine approaches 1, cosine approaches 0, the bottom, cosine is on the bottom, tan is sine over cos. If cos is on the bottom, okay, and it's approaching 0, tangent's going to get very, very big. That's like when the same as we looked at cosecant. It's not the same as a reciprocal, but if the denominator of a fraction gets very, very, very small, the fraction itself is going to get very, very big. So tan approaches infinity, and we have an asymptote, because it's not going to be it's not going to exist when cosine is equal to 0. Okay, and then one of the two, so sine is positive, cosine is negative, so tan has to be negative. Sine approaches 0, so tangent approaches 0 because sine is in the numerator. And then they're both negative. Sine and cosine are both negative. Two negatives make a positive, so tangent is positive now. And see how, if we think about the nature of sine and cosine, we can develop tangent as well. If we think about fractions and the nature of the number as a fraction, right? So whenever sine and cosine are equal, so these are both -1 here, so -1 over -1 is 1. These are the same number here, okay? But one's negative and one's positive, so tangent is -1. These demos will get posted to the classroom, and if you want to play with them, that would be a great idea, thinking about sine over cosine and how that gives us tan, this curve that doesn't really look like secant or cosecant. It's a different kind. It's got this repeating pattern. And so thinking about where the asymptotes are, and the period of tan is actually something else that you could think about. What is the period of tan? It's a little bit different.